In this video, we're going to be looking at the second part of topic 13, a chemical equilibria, and this is part of the IA2 chemistry course offered by Edexcel. So this time, rather than looking at how we calculate Kp and Kc, we're going to be looking at how they are affected by the different factors that can affect equilibrium. So we'll be looking at the effects of temperature, the effects of a catalyst, pressure, and concentration. We will also be looking at how we can link the equilibrium constant Kc or Kp to the total entropy value, and then link that in an equation using the gas constant. And then lastly, being able to apply what we know about equilibrium constants to predict the extent of which a reaction takes place. So we're actually going to start off with the last learning objective of this topic, and then we will revisit it at the end again. I think it helps to look at this one at the start so that you get an understanding of what these numbers actually mean. So there is no hard and fast set rule about the relationship between the position of equilibrium and the equilibrium constant, but in general, the following rules will apply. If we have a very large value of K, whether that's Kc or Kp, a large equilibrium constant tells us that the position of equilibrium is well over to the products, i.e. the position lies very far to the right. If we have a small value of K, again Kp or Kc, this suggests that the position of equilibrium is well over to the reactants, which is to the left. And this links again to the feasibility because it links the value of K in feasibility with the equation linking it to entropy, and we'll come back to that part later on. So what we can do is we can start to look at a table, and this can tell us the prediction of the extent that the reaction might occur. So the smaller the value of the equilibrium constant, the less likely the reaction will occur, because your position of equilibrium predominates in the reactants. The higher the value of K, the more the equilibrium sits towards the products, therefore the more likely your reaction will go to the point where the equilibrium sits so far, it means the reaction goes to completion. So the first factor that we're going to look at in terms of Kp and Kc is the most important one, and that is temperature. Temperature is the only factor that can affect the equilibrium constant of Kp and Kc. The others don't affect it, and we're going to see what that means for the position in just a few minutes. So first of all, if we look at this reaction here, we've got an exothermic and an endothermic. So we have the exo being our production of ammonia, and our endothermic being the breakdown of nitrogen, dinitrogen tetroxide into the NO2. What we can see when we calculate Kp at different temperatures, so at 298, 400, 500 and 600 Kelvin, we can see that the value of Kp decreases as the temperature increases. And for endothermic reactions, the value of Kp increases as the temperature increases. So it does depend on whether it's exo or endothermic, and we see these trends for both Kp and Kc. So exothermic, Kp decreases as the temperature goes up. Endothermic, Kp increases as the temperature goes up. Now, if the equilibrium constant changes with temperature, then the position of equilibrium also changes. So if we take the equation of hydrogen plus iodine to give us 2 moles of hydrogen iodide, which again we've seen multiple times throughout this topic, we can look at the data. So at 500 Kelvin, we have our different numbers of moles, and we calculate Kp to be 160. At 700, we calculate Kp to be 54, based on these numbers of moles. So what we see is as Kc or Kp decreases, the percentages of the reactants increases. So we go from 0.14 to 0.21 for both the hydrogen and the iodine, whereas the hydrogen iodide goes from 1.72 to 1.58. This tells us that our equilibrium is going to shift to the left, and in this case this is the endothermic direction because this forward reaction is exothermic. And we've just said on the previous slide that if we have an exothermic reaction, Kp decreases as the temperature increases. And that's exactly what's happening here. So this shows us that our equilibrium is shifting to the left to favour the endothermic reaction as our temperature is increasing, giving us that smaller value for our equilibrium constant. And we see this regardless of whether it is Kp or Kc. Now, we already know that the position of equilibrium changes when the concentration of a component is changed. And what we're going to look at now is the effects of concentration, pressure, and temperature, and now actually be able to explain them in terms of Kc. So we're not just being as vague as it shifts right or it shifts left, we're now actually starting to quantify it. Now, in an exam, you will likely be asked to calculate a Kp or Kc and then comment on that in terms of a shift. Now, you may not be asked to calculate a new value, but what you can do is you can just put random numbers onto your values to help you figure out which way you're going to shift. And we'll do that at points throughout this video, and you'll see what I mean when we go into more detail with the past paper questions. The most important thing that you can do is you must remember that temperature is the only thing that is going to affect the equilibrium constant. Although the pressure and the concentration can affect the position of equilibrium, it is not going to be affecting the actual value of the constant. So one thing that most people don't understand is when you change a concentration or a pressure, most people look at it as that Kc changes, or why doesn't Kc change? We actually want to flip that question, and we want to say, in order to keep Kc or Kp constant, what happens to the position of equilibrium when I change a pressure or concentration? So we need to make sure we get the cause and effect the right way around. The position of equilibrium shifts for pressure and concentration in order to keep Kc constant. And again, we will start to put some numbers on this so that we can see why this is happening. So one thing that we need to be aware of is a new constant known as Qc. So when the concentration of a component is altered, we get an immediate change in this thing called the reaction quotient, and this is termed Qc. Now, it's very similar to Kc in the fact that it's calculated in the same way. The main difference is that Qc is a measure of the concentrations of the products at reactants in a reaction at any given time. So Kc is at equilibrium. Qc is at any point in the reaction, typically right after you've made a change to one of your concentrations. So when we get this change, our reaction quotient, or Qc, is now different to Kc. And what we do is we shift our position of equilibrium to change our composition until Qc, our reaction quotient, so those concentrations at any time, now equals back to Kc. Because Kc cannot change. So we're shifting the position of equilibrium to get back to that value. So for the same general reaction that we've seen in the previous video as well for this topic, we've got Wa plus Xb is in an equilibrium with Yc plus Zd. So our Qc is still the concentration of C to the power Y and D to the power Z over concentration of A to the power W times B to the power X. The only difference is that these are not necessarily at equilibrium, so we have no EQ subscript. So we've seen in the part 1 video where if it's at equilibrium you might have a subscript of EQ. Here we don't have this because it can be at any time. And at equilibrium, these two values will equal each other. And this is where we want to always get to. So whenever we change concentration by amending the pressure or whatever it is that we change, we always want to get back to Qc and Kc being equal. So if we look at the reaction between hydrogen and iodine to form hydrogen iodide, so we've seen again this same equation multiple times. We want to explain the effect of the position of equilibrium of increasing the concentration of hydrogen at a constant temperature and pressure. So we've got two different things here. We have Kc and we have Qc. Now what I'm going to do to help us understand this is I'm going to pick random numbers. And I'm going to say my concentration of hydrogen at equilibrium is 2. My concentration of iodine at equilibrium is also 2. And my Hi is 4. So my Kc is going to be 4 squared over 2 times 2, which gives me a Kc value of 4. If I suddenly increase my concentration of hydrogen, then I'm going to measure the Qc now. So my reaction quotient, now I am out of equilibrium. So in this case, I'm going to say that H2 becomes 10. So for my Qc, this now becomes 4 squared over 10 times 2, which gives you a value of 0.8. So now my Qc is going to be less than my Kc. And this is a problem because we want to get these two things back to being the same. So what we have to do is we have to look at, well, what change do I have to make in order for Qc and Kc to come back together? And you can see that it's going to require us to increase the numerator. And you could even show this by saying Qc is going to be equal to x squared over 10 times 2, but we want that to be equal to Kc, which is equal to 4. And when you rearrange that, your x is going to have to be increased up to 8.9, i.e. my position of equilibrium is going to have to shift to the right to increase my concentration of my hydrogen iodide up to 8.9 to now counteract the fact that my hydrogen concentration has went up to 10. So in order for Qc to no longer be less than Kc, I need to increase the value of my numerator, meaning I need to increase the concentration of my products. And to do that, the equilibrium is going to shift to the right. It's going to continue to increase my products until the value of Qc becomes equal to that of Kc, and now I get my new equilibrium. Remember, my concentrations do not have to be do not have to be equal, they must be constant. So I just now am shifting from one equilibrium, shifting to the left until I reach a new equilibrium. And this is the same thing that we probably would have predicted in topic 9 when we were looking at the qualitative prediction. So we're saying as we increase the concentration of H2, my position of equilibrium is going to shift to the right. All we're doing now is we're explaining why. And it's because Qc, when we have that increase in the hydrogen, becomes less than Kc. So we need to increase our numerator, or concentration of our products, in order to make Kc and Qc the same. So we're just simply quantifying the process. Now sometimes the qualitative predictions that we make are not always correct. So we may have previously made a qualitative prediction just basically looking at the number of moles or looking at the concentrations and determining what the shift is. The problem with this is that sometimes we need to use a calculation because we may have two competing factors and we don't know which one is the biggest. And we did see this in our topic 9 where we looked at the limitations of the qualitative predictions. And if you can't quite remember, go back and have a look at the video and it goes through some of the bullet points about that. Now, because we're giving it a quantitative value, we can now do the predictions. So if we have the Haber process here, so nitrogen plus hydrogen giving us the 2NH3, we've got our number of moles in our equilibrium mixture, and our total volume is 1 decimeter cubed. We want to work out the direction of the shift in equilibrium if we add 0.14 moles of N2 to the system. And we want to show all of our calculations. And it gives us our Qc value. So how are we going to do this? Well, the first thing that we have to do is we have to calculate Kc. So Kc is going to be our equilibrium concentrations. So that was 0.204 for the ammonia divided by the volume of 1, and that is going to be all squared, over the 0.510 over 1 of the nitrogen times the 0.197 over 1 cubed for the hydrogen. So my Kc value is 10.7. Now when we add in our number of moles of the nitrogen, we're now getting a difference in our the total number of our moles. So our moles of gas at our equilibrium was 0.51 plus 0.197 plus 0.204, giving us 0.911 moles. The problem is now I'm now adding in this 0.14 moles of the nitrogen. So my new moles is 0.911 plus the moles of nitrogen that I have added, giving me a total of 1.051 moles of gas. You may be wondering, why are we calculating that? Well, we now need to calculate our change in our volume. Because the pressure is remaining constant, we are getting our gas mixture expanding, so our volume must be expanding. So we're going to assume that this gas mixture behaves like an ideal gas, so then our volume of our gas is proportional to the number of moles. So we would use our original moles over our original volume is going to be equal to our new moles over our new volume. So that would be 0.911 over 1 is equal to 1.05 over V2, and I can then rearrange and cross multiply to find my new volume is 1.154 decimeters cubed. So now I have that new volume, what I can now do is I can calculate Qc at the moment that the nitrogen is added. So our Qc is going to be our 0.204, because that's not changed for the ammonia. This time it's over the 1.154 volume, and that is squared. That's going to be over our new concentration of nitrogen is 0.650 over our volume, multiplied by the hydrogen, which concentration has not changed, over the new volume, and that is all cubed. And that is going to now give me an answer of 11.15. So this time, Qc is going to be larger than Kc, because I had 11.15 versus 10.7. So in order for me to get back to my equilibrium and to re-establish, I have to reduce the number for the Qc. So in order for my number for Qc to reduce, I have to increase my denominator. And in order to increase my denominator, I have to shift my equilibrium to the left, meaning I'm shifting towards my reactants. Now this is different to what we would expect. We're saying that if Kc is larger than Qc, I must increase my denominator this time, as opposed to last time where we increased the numerator. So I'm shifting left to my reactants, which is what we're confirming here. So Qc must decrease. I need to increase the denominator, shifting left. Now, our prediction would tell us that the equilibrium should shift to the right, away from the nitrogen. We're saying if we add in nitrogen to our reaction, it should shift towards the ammonia. So this is where our qualitative prediction fails us, and we go off of the quantitative one. And the problem with making the prediction is the fact that we're getting two conflicting changes here. By increasing the number of moles of nitrogen, that's pushing the equilibrium to the right. But the other thing is that we're increasing the volume, and increasing the volume is going to give you a decrease in pressure, which should shift the reaction to the left. So because we have two competing shifts, we don't know which one predominates unless we do these calculations. So again, this is what we mentioned back in topic 9, that we don't know which one has the bigger effect, but if we do our QC and Kc calculations and compare them, now we do know. So now what we can do is we can start to build up a pattern here. So if we have our QC value, our reaction quotient, being less than our Kc, we're going to get our equilibrium shifting to the right. And this is because we need an increase in our numerator. And that was when we saw in our first example where we had the H2 plus the iodine giving us the hydrogen iodide, and we increased the concentration of the H2. Whereas in this expression, our Kc was less than the QC, so our QC is larger, meaning it is going to shift to the left because I need to increase my denominator. And this was what we seen when we had the hydrogen and the nitrogen forming the ammonia when we increased the concentration of nitrogen. So if our QC is smaller, it is going to shift towards the products. If our QC is larger, it shifts towards the reactants. And that's the general pattern that we start to see as we do these calculations. And this will then allow us to start making these quantitative predictions. Now, similar to concentration, our change in our pressure on an equilibrium system that contains gases has no effect on the Kc and the Kp values. Any change in the equilibrium constant occurs to maintain this. So we have our change in our position of equilibrium to maintain our Qc and Kp. Exactly the same as we've seen for the concentration. So if the partial pressure of one component gas is then changed, then the overall effect on Kp can be predicted in the same way as we just did for the concentration. But what we need to understand is that the total pressure of the gaseous system changes, which then causes all of the partial pressures to change as well. And that effect on the position of equilibrium can be explained again using equilibrium law. So if we stick with our Haber process, so our ammonia reaction, we have got our nitrogen reacting with the 3 moles of hydrogen to give us our 2 moles of ammonia. We can then express our Kp and using equilibrium law, and then we can then make it a little bit simpler, and we can express the partial pressures of nitrogen, hydrogen and ammonia as A, B and C atmospheres. So we get this new, more simplified Kp expression. If we double the total pressure, our partial pressures of nitrogen, hydrogen and ammonia are also going to double. So they become 2A, 2B and 2C. Now we use these values to calculate our QP, so our reaction quotient. We are now out of equilibrium and we need to see what's happened to our ratio between our reactants and products. So when we put in these new values, we get this new QP expression. And when we potentially put numbers into this, what we see is that QP is now 1/4 the value of Kp. So Qp is smaller than Kp. So in order to re-establish our equilibrium, we need to increase our numerator, meaning we need to make more products, which is what we saw for Kc. And that will continue to happen with our nitrogen and our hydrogen reacting to form more and more ammonia until QP comes back into balance and is now equal to KP. So an increase in our pressure is going to increase the yield of ammonia because we see that equilibrium shifting to the right. Now, catalysts, we know, don't affect the position of equilibrium. We've looked at this from topic 9. And the reason why is because they don't appear in the stoichiometric equation. Therefore, they don't appear in our Kp or our Kc expressions. So if they don't appear in those expressions, they cannot affect the position of equilibrium. What they simply do is they increase the rate of the reactions and they increase the rate of the forward and the reverse to the same extent, meaning we just get to equilibrium faster. They have no effect on the actual position of equilibrium. Now what we can do is we can start to link entropy to our equilibrium constants. So from topic 12, hopefully you remember that our total entropy is equal to the entropy of the system plus the entropy of the surroundings. And for a spontaneous change, our total entropy is going to be positive. When we get a temperature change, we don't get a very big change to our entropy of the system, but we do see significant changes of our entropy of surroundings because we calculate this using our negative delta H over T. So as soon as we start to change T, that has an effect on the entropy of the surroundings, which therefore affects the total entropy. And there's that knock-on effect. So if we have a reversible reaction, what we are really saying is that we can reach equilibrium from either side. So I could start with, for example, an alcohol plus a carboxylic acid, and I can make the ester and the water and reach equilibrium, or I could have the ester and the water and form the alcohol and the carboxylic acid and reach equilibrium. It does not matter which way I go from, I can always reach equilibrium from either side. So what this tells us is that both the forward reaction and the reverse reaction must be spontaneous, because it must have that positive entropy value for our total entropy in both directions. So we need to figure out, well, how does this work? How is this possible? And we're going to look at our very common reaction that we've covered multiple times here, our dinitrogen tetroxide breaking down into the 2 moles of the nitrogen dioxide. And the reason that we can use this one is because we see colour changes, and it allows us to easily see where our position of equilibrium sits. The carboxylic acid and alcohol with the ester and water is a little bit trickier because we can't see the formation of the ester and it's not as easy for us to figure out our number of moles. Whereas when we use things that have got a colour change, we can easily see where the position sits. So at room temperature, we've got a mixture of the two and we have this pale brown colour. In hot water, we get a darker brown, and you can see that our volume has increased slightly, whereas in crushed ice or a cold temperature, our volume has decreased and we have become paler. So how do we explain this? Well, in hot water, the mixture is getting darker, so our equilibrium is shifting to the right, meaning we are making more of our NO2 because that's our brown substance. And this is because our volume is larger, because as it gets warmer, our mixture is expanding. In cold water, the mixture gets lighter because our equilibrium is shifting to the left, making more of the colourless dinitrogen tetroxide. And our volume is smaller because the reaction mixture is cooled. So remember, volume expands as it gets hotter. As it gets smaller, the reaction mixture as it gets colder, the reaction mixture gets smaller. So when we start to look at the levels of entropy, when we start with the pure nitrogen tetroxide, our forward entropy is a positive value up to our equilibrium mixture. So this part in the centre here. If we start with the pure NO2, the entropy for our backwards reaction is also positive meaning both of these are spontaneous reactions. So because the entropy of the N2O4 is less than the equilibrium mixture, and this is to do with the fact that we're getting more particles being formed, so we're getting more disorder, because in our equilibrium mixture we're going to have potentially 3 moles, 1 mole of our reactants and 2 moles of our products, whereas for our products we only have 2 moles and our reactants we only have 1. So that increase in the number of moles is going to give you that positive entropy change. So the change from the pure NO2 to equilibrium is positive, so the reaction is spontaneous. The change in entropy from the pure NO2 to the equilibrium is also positive, so the reaction is also spontaneous. So the entropy change for the mixture of the two gases in any proportions moving to the equilibrium is always positive, meaning I can reach equilibrium from either side of the reaction. Now, at the position of equilibrium, our total entropy change is 0. Our total entropy of the forward equals the total entropy of the backwards reaction. So now what we can do is we can start to relate total entropy to the equilibrium constant, and we use this equation here. So delta S total is equal to R, the natural log of K. K can be Kc or Kp, just depending on whether you're looking at pressures or concentrations. And R we know is the gas constant, and we've already seen that being used in PV equals nRT. And we know that R is equal to 8.31 joules per mole per Kelvin, and that will be given to you in the data book or in the question. And we can then either use this calculation to calculate the entropy, or we can calculate the equilibrium constant by rearranging it so that K is equal to the exponential of the total entropy over R. So the equation for the reaction to form sulfur trioxide from sulfur dioxide and oxygen is shown here, and we have our total entropy given to us. And we want to calculate the value for the equilibrium constant. So we've just said the total entropy is equal to R, the natural log of K, and when we rearrange that, K is equal to E, the total entropy over R. So K is equal to E, and you find that E on your calculator, the exponential. So E to the power of 238.3 divided by 8.31, and K is then calculated to be 2.84 times 10 to the 12. So if we now go back to where we started, what we said was that the position of equilibrium can be determined using K. So the very large value of K suggests that the position sits all the way over to the products. The small value of K tells us that the position of equilibrium lies well over to the reactants, and this is because of this S total equal R ln K value. The smaller our value of K, the less positive our entropy is going to be, meaning we're going to have potentially have our reaction not go at all. Or the larger the value of K, the more positive the entropy, meaning the more likely the reaction will be spontaneous. So this is where we start to link this feasibility table, where our total entropy increases as the magnitude of our equilibrium constant increases. So as our equilibrium constant gets larger and larger, the reaction becomes more and more spontaneous, to the point where eventually the position of equilibrium is pushed so far to the right that the reaction goes to completion. So if we have any value of above 1 for our Kc, the reaction has a positive total entropy and therefore is a spontaneous reaction. So let's finish off by looking at some past paper questions. So the question is about the thermodynamics of this very, very common reaction. We've now seen this multiple times all the way through, and this would probably form part of a larger question. So in this experiment, we had 10 moles of the dinitrogen tetroxide placed in the closed container, and eventually 27% of it has dissociated, and the pressure was 4 atmospheres. Now, you probably find that part A of this question would ask you to calculate Kp, and in this case, I'm giving it to you because we don't actually want to do that. We want to focus on the other part. So in this case, Kp is calculated to be 1.26 atmospheres. We're saying that we're doubling the total pressure to 8 atmospheres. State the effect on Kp. Well, the most important thing is that Kp is only affected by temperature. Therefore, your answer here for a nice, easy 1 mark has no effect on Kp. Now we're looking at this doubling of the atmospheres from 4 up to 8 at a constant temperature. And we want to explain the change in percentage of dissociation of N2O4 by considering the effects of the partial pressures of NO2 and N2O4. So if we double our pressure up to 8, so doubling the pressure causes our numerator to increase more than the denominator, because our numerator is going to be squared, whereas our denominator is not. The fact that Kp must stay constant means that we're going to have to change our position here. So our Kp is constant, and if our numerator has increased more, what we need to do is we need to increase the fraction of our N2O4. So for our Kp to stay constant, we must increase the mole fraction of the N2O4, meaning we have to make more of the N2O4. So therefore, our percentage of dissociation of the N2O4 is going to decrease, because we want less and less of it to be dissociating as we want to be making more of it. So you get your 3 marks for breaking it down. So what happens to your numerator and your denominator, i.e. what's your Qc value going to do? In order to keep Kp constant, what is our position of equilibrium going to do? Well, in this case, it's going to shift to the left. Therefore, what does that do to our percentage of dissociation? It's going to decrease. Again, another one, we want to consider the following reaction. So this time we're starting with the 2 moles of the Hi, and we're going to the I2 plus the H2. And in this time, our I2 is a solid, so it's not included in our Kp expression. We are given the Kp expression, and we want to use that to explain the increase in the effect of the total pressure on the position of equilibrium. So this is where you could start to give random numbers. So if I have H2 and Hi, I'm going to say that my mole fractions are 2 and 4. Just pick nice, easy numbers. If my pressure is 6 atmospheres, my partial pressures are going to be 12 and 24. So Kp is going to be equal to 0.021. If I now change this to be 12 atmospheres, so increasing my total pressures, my partial pressures go up to 24 and 48. So Kp is coming down to 0.01. So now that I've brought my Kp, this would be my Qp. So now what I'm seeing is that my Qp is less than my Kp. So when this happens, I'm going to get a shift in my equilibrium to the right, because that's what we saw. So how do we explain this? Well, the first thing is we want to say that Kp is constant. That's the most important thing. Because Kp is constant, now we get that shift in our equilibrium. So when we increase the pressure, our Qp value is going to decrease, i.e. Qp is less than Kp. So in order to restore Qp being equal to Kp, I need to shift my equilibrium to the right, because I need to make more of my H2. I need to increase my partial pressure of my H2, or my proportion of my H2. So my equilibrium is going to shift to the right. These are the mark schemes for those questions if you've been trying them at home or you want to see how the marks break down. That's everything for topic 13A, chemical equilibria. I would strongly suggest that you practice being able to calculate Kc and Kp, and not only that, now be able to calculate Qc and Qp and relate those two numbers together and be able to then explain what way the position in equilibrium shifts when you get that change in pressure or concentration. Please do remember that the only thing that will affect your equilibrium constant is temperature, and you should really state that in all of your responses, because that generally will get you a mark. If you have any questions, please feel free to leave a comment below, and we hope to see you back soon.